In this lesson, we will delve into Task 2.1 of Project 2, which focuses on the boring machining technology and precision hole machining tools, specifically the principles of boring machining and boring tools. We will explore the principles and the characteristics of boring machining, as well as familiarize ourselves with various types, structures, and applications of boring tools. By comparing drilling and boring, we will experience the transition from approximate to precise and appreciate the importance of precision measurement and accurate adjustment in modern industry. In the field of metal cutting, boring is a very important machining method. In Task 2.1, we will focus on learning the principles of boring machining and boring tools. Principles of boring machining. Boring machining is a process that uses a boring tool to remachine an existing hole to improve its dimensional accuracy, shape accuracy, and surface quality. During boring, the boring tool performs the primary rotational movement, while either the workpiece or the boring tool performs the feed movement. Compared to drilling, which is a rough machining method primarily used to create holes in solid material with relatively low precision, often only meeting approximate size requirements, boring is a finishing process that achieves the transition from approximate to precise. From the perspective of motion principles, the primary movement in boring machining is the rotational movement of the boring tool. The feed movement can either be the linear movement of the workpiece or the axial movement of the boring tool. This type of motion allows for precise trimming and machining of the hole. In practical applications, such as machining cylinder bores in engine blocks, the requirements for dimensional accuracy and cylindricity of the holes are very high. Drilling cannot meet these requirements, so boring machining is necessary. Through boring, the dimensional accuracy of the holes can be controlled within a very small tolerance range, and the cylindricity can also reach a high standard. High precision, boring machining can achieve high dimensional and shape accuracy. Generally, the dimensional accuracy can reach IT7 to IT6 levels, and the surface roughness RA value can be as low as 1.6 to 0.8 micrometers. This is because during the boring process, the cutting edge of the tool can precisely control the amount of material removed, and the machining accuracy can be gradually improved through multiple passes. Capable of machining holes of different diameters and depths, boring tools can be adjusted as needed to machine holes of various diameters. Boring also has excellent adaptability for deep hole machining. For instance, when machining the spindle holes of large machinery, which often have large diameters and significant depths, boring machining can effectively accomplish the task. Can correct axis errors of existing holes. If there are axis deviations or other errors in the existing hole, boring can correct these errors by adjusting the position of the tool and the cutting parameters, ensuring the axis accuracy of the hole. Types and structure of boring tools. 1. Single-edge boring tool. A single-edge boring tool has only one cutting edge, making it simple in structure and easy to manufacture. It can be ground to different geometric angles according to machining requirements. It can be divided into through-hole boring tools and blind-hole boring tools. Through-hole boring tool, used for machining through holes, its main cutting edge angle is generally between 45 degrees and 75 degrees, and the secondary cutting edge angle is between 15 degrees and 30 degrees. This type of boring tool exerts relatively small cutting forces during machining, which is beneficial for improving machining accuracy. For example, when machining through holes in general mechanical parts, a through-hole boring tool can be used. Blind-hole boring tool, specifically designed for machining blind holes. Its main cutting edge angle is generally between 90 degrees and 100 degrees to ensure it can reach the bottom of the hole. When machining blind holes, the blind hole boring tool requires a special structural design to avoid interference between the tool and the hole bottom. The advantage of a single-edge boring tool is that it allows for manual adjustment of the tool's position to accommodate different machining requirements. However, its drawback is lower cutting efficiency, as only one cutting edge is engaged in cutting at any given time. Double-edge boring tool. A double-edge boring tool has two symmetrical cutting edges, which allows the radial forces to balance each other during cutting, thereby reducing the deformation of the workpiece. Common types of double-edge boring tools include fixed double-edge boring tools and floating double-edge boring tools. Fixed double-edge boring tool. Its two cutting edges are fixed on the tool body, providing high dimensional accuracy. Fixed double-edge boring tools are widely used when high machining accuracy and large batch production are required. For example, in the production line of automobile engine blocks, fixed double-edge boring tools are used to machine cylinder bores. Floating double-edge boring tool. The boring inserts are mounted on the tool shank through a floating structure, which can automatically compensate for tool installation errors and workpiece bore diameter errors. During machining, the inserts can float within the slots of the tool shank, allowing the cutting forces to automatically balance, thereby improving machining accuracy. When machining holes in thin-walled parts, floating double-edge boring tools can effectively reduce workpiece deformation. Fine adjustment boring tool. A fine adjustment boring tool is a high-precision boring tool that allows for precise adjustment of the tool's size through a fine-tuning mechanism. The fine-tuning mechanism of a fine adjustment boring tool typically uses a threaded pair or an eccentric mechanism. In practical applications, when precise fine-tuning of hole dimensions is required, fine adjustment boring tools play a crucial role. For instance, in mold manufacturing, fine adjustment boring tools are necessary to ensure the dimensional accuracy of some high-precision holes. Selection and application of boring tools. When selecting a boring tool, several factors need to be considered. The first is the size and the precision requirements of the hole to be machined. If the dimensional accuracy requirement is very high, a high-precision boring tool, such as a fine adjustment boring tool, should be chosen. Secondly, the material and shape of the workpiece must be considered, as different materials require different tool materials and geometric angles. For example, when machining materials with higher hardness, tool materials such as carbide should be selected. In actual production, the application of boring tools is very extensive. In the aerospace field, boring is used to machine key engine components, such as the mounting holes for turbine blades, where the precision of these holes directly affects engine performance. In automotive manufacturing, boring is used to machine holes in components such as engine blocks and transmission housings. The importance of precision measurement and accurate adjustment. In boring operations, precision measurement and accurate adjustment are key to achieving precise machining. From an ideological and political perspective, this reflects the transition from approximate to precise. In rough machining processes such as drilling, the precision requirements for measurement and adjustment are relatively low. However, in fine machining processes like boring, precision measurement is essential. For instance, when machining high-precision holes, tools such as micrometers and calipers are needed to measure the hole dimensions in real time. Based on the measurement results, precise adjustments to the boring tool must be made. Only in this way can the dimensional and shape accuracy of the holes be ensured, meeting the demands of modern industry for product quality. Case study. Taking the machining of an automobile engine block as an example, the engine block contains multiple cylinder bores, which require very high dimensional accuracy and cylindricity. During the machining process, a drill is first used to create an initial hole. Then, a boring tool is employed for the boring process. Throughout this process, precision measuring equipment is used to monitor the dimensions and shape of the holes in real time. If any deviations in the hole dimensions are detected, the position of the boring tool and the cutting parameters are promptly adjusted. Through this process of transitioning from rough machining to fine machining, and from approximate to precise, the high precision requirements of the cylinder bores are ultimately ensured, thereby enhancing the performance and the reliability of the engine. In this lesson, we learned about the principles of boring operations and boring tools. We first explore the principles of boring, which involves remachining an existing hole. The primary motion is the rotation of the boring tool, while the feed motion can be the movement of either the workpiece or the boring tool. Boring operations are characterized by high precision, the ability to machine holes of various diameters and depths, and the capability to correct the axis errors of existing holes. We then examine different types of boring tools, such as single-edge boring tools, double-edge boring tools, and fine adjustment boring tools, and learned about their structures and applications. When selecting a boring tool, factors such as the size and the precision requirements of the hole, as well as the material and the shape of the workpiece, must be considered. Finally, we emphasize the importance of precision measurement and accurate adjustment in boring operations, and through case analysis, we appreciated the transition from approximate to precise. I hope everyone can deeply understand these key points and apply them flexibly in practical situations.